We're now going to take a look at an example application of Java Phaser. Hopefully this will put the pieces together and lead to less confusion than just looking at the methods by themselves. And this is a fun example that you can take a look at. And it basically expands upon the super duper pithy examples you get in the Java documentation. The Java documentation is very, very sparse explaining how this stuff works. So I came up with something more interesting to show how to do this. And this showcases phasers that are used as entry and exit barriers in addition to one-shot and cyclic barriers. And you can get this code here at this link in my live lessons GitHub repository. So here's the test program. There's a factory method called makeTasks, which makes a list of my task objects. Don't worry too much about what my task objects are. They're just simple things here to demonstrate how phasers work. And the main thing that this does is it creates a number of values from 1 to the number of tasks. Let's say we have 10 tasks. It goes ahead and makes a new task object where each one knows its number from 1 to 10, and it collects those things into a list. So we end up with a list of my task objects. Here's where it gets fun. So we're going to have two examples. We're going to have one called run one-shot tasks, which will take the list of tasks and run one-shot tasks. And then we're also going to run cyclic tasks, which takes a list of tasks and runs them for this number of iterations. Let's say the number of iterations is 5 or 10 or whatever. So not surprisingly, this is going to do one-shot tasks with an entry and an exit barrier. And this is going to do cyclic tasks with a phaser, which works as a barrier. So let's start out by taking a look at the one-shot phasers that use entry and exit barriers to run a list of tasks simultaneously. And this is kind of a neat example. So we take the list of tasks and we create an entry barrier phaser that has an initial value of 1. So that means that it's registering the thread that will initialize everything. That's basically everything from here down to that line called arrive and deregister. And this particular entry barrier is very, very similar to a cyclic barrier, but a little bit more flexible, as you'll see here in a second. Then we create ourselves an exit phaser, which is going to be initialized to the number of tasks. So let's say we have 10 tasks, so we're going to have a phaser that has a value of 10. Then we go through a for each method, which will iterate through all the tasks, and for each task, we're going to dynamically add a new party to the entry barrier. This is how things differ a bit from cyclic barrier. With cyclic barrier, you have to know ahead of time exactly how many barriers you're going to have or however many parties you're going to have. In this case, we just register them as we need to. So for each task, we're going to register it, or we're going to indicate to the entry phaser that there's another task that wants to be part of this. And then we go ahead and we make ourselves a new thread and start it. And this is a worker thread that's going to run the task, here's the task run method, in a background. And the way this works is it calls entry phaser.arrive and await advance, and that will block until all the worker threads are started up. So every one of these worker threads, let's say there's 10 of them, they're all going to start up and wait here to begin to run. So that's very much like the await call on cyclic barrier. This code uses entry phaser, this guy, as a one-shot entry barrier. The next example will show you how to do it with cyclic barriers. So once they've all been started, once they've all reached this barrier entry point, they all start running in parallel. So the task run method is called back. It does whatever the heck it does. We don't really care. It's not important. And then they're all going to call the arrive method. And arrive just says, hey, exit phaser, we're done. So it's kind of like a countdown on a countdown latch. And what we're going to see here is the following. So all these guys start up running, and then the entry phaser arrives and deregisters. And so basically what that says is we're going to decrement the count by 1. So as these guys, so let's say, again, there are 10 of them. After all 10 arrive, then they will start to run. This guy arrives and deregisters, so it decrements the count from this 1 here to be 1 less, but these guys here, this is done in order to make sure these guys can get started up and they'll block. So the worker threads can start running their tasks, and then the initialization thread calls await advance on the exit phaser passing in a 0, because initially the phase of any phaser starts at 0, and what this is saying is block until all the threads have arrived at the exit phaser, which will then, when the final thread, thread 10, or whatever thread finishes last and calls arrive, that will trigger the phaser to advance to the next phase, so it'll no longer be at phase 0, it'll be at phase 1, and then await advance will return when the phase of the phaser, the exit phaser, no longer matches the parameter that's passed in. So you can think of this as basically kind of like countdown latch await. Okay, pretty simple. You could arguably have done the same thing with a cyclic barrier. Probably would have been about the same. Probably would have been a little bit cleaner, actually. But the nice thing about this approach, as you saw, is we can dynamically register these tasks. We don't have to know how many there are in advance. That's one of the main benefits of this approach. Whereas we needed to know the number of parties for a cyclic barrier when we created the cyclic barrier. So that's one advantage. Now let's take a look at a more powerful use case. This is going to be showing how to do cyclic barriers and cyclic tasks. So here we have the list of tasks like we did before, plus an iteration count. The example here is in EX26 in my Live Lessons GitHub repository. We start out here by creating a phaser that's going to run a given number of times. What's that number of times, you ask? Well, we're going to dictate that by our implementation of the onAdvance hook method. And you can see here that onAdvance says if the phase plus 1 equals the number of iterations. And the reason we have to add 1 is because phase starts at 0. So if iterations are 10, and we say phase plus 1 equals iterations, that returns true, then we're done. So what we say here is after we've run the 10th iteration, then shut yourself down. So that, in this case, determines when the phaser will be done. Or all the parties have gone away. In this case, it's when the iterations equal the number. For fun, because we don't want to always do the same boring thing, we're not going to explicitly call register for each task. Instead, we're going to bulk register everybody up front. So you can see what we do is we take the number of tasks, add 1 to it, because we want to do that for the initialization thread that's doing the initialization here. So we're basically, let's say we have 10 tasks. We're going to have a bulk registration of 11 parties into this phaser. We're then going to iterate through all the tasks, and for each task, we're going to make a new thread and start it, and that thread is going to have a do while loop, which is going to run the task, and then, we don't care what it does, and then we're going to go ahead and call arrive and await advance. So this call here is going to block until all the threads have reached that point. And it's going to keep doing this. Oh, so that's using it as a cyclic exit barrier, because we're going to, we did this so that run happens first no matter what, and then we wait to see if we need to advance, or we wait to advance. The last thread to arrive at the end of a phase triggers a call to the onAdvance hook method, which then checks to see whether the phase plus 1 equals the number of iterations we want to do. And if that's the case, onAdvance returns true, in which case the phaser is considered terminated. And each thread runs a do while loop that keeps running while the phaser is not terminated. So while the phaser has not shut down, in other words, while we have not reached the end of the iterations, it's going to keep looping. So each thread will keep looping, doing this computation until the phaser is shut down. The calling thread, which I've been calling the initialization thread or the orchestrator thread or whatnot, just runs a while loop that says while the phaser is not terminated, phaser arrive and await advance. So it's throwing itself into this mix, and we can do that because we added 1 to the bulk registration to keep track of this thread. So this thing will keep looping until everybody's shut down. Now, arrive and await advance blocks until the phase has completed. So this loop, and for that matter, this do while loop, is not a busy wait. It's just blocking at the arrive and await advance method. When that returns, we then check to see if we've been terminated or not. And if so, we're done. Otherwise, we keep looping and call arrive and await advance in the case of the initialization thread, or in the case of the worker threads, we call run, and then we call arrive and await advance. Okay, so that's the end of the example that demonstrates both one-shot entry and exit barriers using phasers, which, as again, we saw that was maybe a little overkill. We could get the same effect with a cyclic barrier. But then we also showed the cyclic stuff here where we bulk registered things, and we could have these different loops, and we had the on advance stuff. So you can start to do more powerful and more interesting types of barrier synchronization using phasers. Having said all that, for the most part, you can get by with cyclic barriers and countdown latches in practice. But phasers come in handy if you don't have a known number of parties when any given phase is starting out.